Today we have with us Rishi Paresh Joshi, a third year integrated MSc student. He will be giving a talk on topological phases of matter. Over to him.
Thank you for giving me this opportunity to give the talk. Firstly, I'd like to introduce myself. So, I'm third year integrated MSc, and I had done my summer internship under Professor Rishi Paresh, who is actually a person who had done his PhD under JPG. And he is one of the pioneers in the field of quantum Hall effect, the fractional quantum Hall effect, which is still open research problem. So this was, I think, a month and a half long internship, and I learned a few more things than what is there on the talk. There are some things which I had not learned there and I learned recently. But I tried to make the talk concise and as heuristic as possible. There is some math towards the end. Some of it even I don't understand very well because I'm still studying. I'm very new to this topic. But whatever heuristically I understood and whatever I understood by connecting few dots by reading different books, I have presented in my own way. So this is a table of contents. I will be talking about in the introduction. I will be talking about basically what condensed matter deals with, because I feel that is it gives a more purpose to what I'll be covering next. Then there is the classical Hall effect, there is the integer quantum Hall effect. Then I will be talking about topology and integer quantum Hall effect. So this will be somewhat related to what I will be talking about in the introduction. And then there are some applications of topological insulators. Right now it has not been these ideas, these materials and their properties have not been introduced into industry because of some of the shortcomings, but in future we hope that there will be some more applications. Okay. So introduction. So in introduction, what happens in the real world? So I had mentioned, I think in the mail that I would love to welcome people from other streams as well. Mainly because I felt that the concept of emergence is somewhat related to biology and in some sense chemistry and other fields as well. Because of the fact that many particles, when they come together, they have a completely different picture to explain them. And it's not so trivial as just saying that two particles have some force or some interaction between them. And that is the phases in condensed matter physics. So I'll be talking about some research going on in this field very briefly because I myself don't know much, but just the idea. And then I will talk about what the topological phase of matter is. That also in a very naive way. Okay, so basically, this is the kind of the scientific method I've written down. But now in the modern world, I feel it has some more alterations because we need funding to perform this. So I have structured it in this way. You observe natural phenomena, you try to explain it by some hypothesis, you test the experiment by hypothesis by proving it whether it's wrong, and over time, the hypothesis become fundamental. Still here we know it's a scientific method. Now what is the next step is that these fundamental laws have to also go back into application in the industry. Can be either for improving a human life or if you're talking in terms of research, it is also to improve the precision of the instruments we use in experiments. So that's why we have got a lot of these quantum sensors and which prove magnetic examples to explain what I just showed previously is what we have, like, say, quantum engineered devices. Okay, like ultra cold atoms. So these are like Rydberg atoms. Examples: Rydberg atoms. So they are rubidium atoms, and one of them is, say, excited to around very high energy levels. So the atoms which are surrounding the excited atom, okay, they cannot be at a excited state. They have to be at the ground state. You can think of it classically as Coulomb repulsion, but the specific term used there is called Rydberg blockade, because the overlap of the integrals, okay, it vanishes. Then Rydberg atoms, trapped ions, and there is a superconducting qubit. In terms of quantum dynamics theory, we have like quantum chaos. So that talks about like how we have in classical mechanics, we have integrable systems. So it's analog in quantum mechanics, non-equilibrium phases. Like you have, for example, time crystals. So these are crystals which, if I'm not wrong, they preserve the entropy of the system. So they are candidates for storing memory in just a very small piece of matter. They can store in very large, maybe probably all combined knowledge of it. So that kind of a system. And then quantum algorithms like the Grover's algorithm, the Shor's algorithm. So yeah, so I had mentioned that the whole is okay. So this is okay. Before I come to that, so reductionist hypothesis. So they say that if you know how the most fundamental particles are behaving, it says that you can tell what are the other, when there are a lot of fundamental particles combined, you can be able to predict all of the physics which will emerge from that. Okay, so that's why this is a small meme or joke. Sociology applied psychology. So this is the maths. This is for a joke, like they require funding from us. So yeah, coming back to emergence. So, emergence, like I said, is a collective behavior of many elementary particles, which cannot be simply derived from their individual constituents. So in other words, what I was saying is, it is that the whole is not equal to the sum of the parts. There are many types. There are two types of emergence. One is epistemologic and ontologic. So epistemologic is like a weak interaction between the particles, that they do not. These interactions can be like actually calculated by a computer. Okay, assuming that you have such a system, and you can model a physical system using that, because there are very weak interactions. And ontological is strong interactions, which actually require a lot more physics coming out of it. Now, I would also like to go a little bit into philosophy. So there is a string theorist called Brian Greene. I read about this in this paper by a Cambridge professor. So in that he mentioned that Brian Greene, a string theorist, believes that once we know what is the fundamental forces between universal coupling between two particles, it is, at least in theory, that you can explain all phenomena. Okay, but now then the conflict in condensed matter comes, where you say that no, that's not quite true, because when you actually consider this is philosophy. So when you actually consider interactions between all the particles, it is also you are trying to explain to your mind how the macroscopic phenomena emerge from these interactions. So it's like saying that these are actually physical laws which have meaning. Although we would say that okay, we are just using the electrodynamics and quantum mechanics. Okay, so that actually leads me to the concept of phase. So phase is something that is like you have the same particles at a you have the same particles in a medium which is completely homogeneous and all the physical properties are the same. That's what we call a phase in condensed matter physics. For example, you have a solid phase, liquid phase, gas phase. Actually speaking, if you ask me to define what a phase is, it will be really hard for me to do so. And there have been many theories related to that. So, some of the theories are this Landau's theory of symmetry breaking, saying that a phase will change when some symmetry in the system is broken. But we know that that is also not entirely true. There can happen a phase change which will not break any symmetry, but there is still a phase change. So, I'll be actually speaking on that. Nothing but the topological, because of change in the topological order. So, phases require some mathematical structures known as renormalization groups for their proper definition. But this is a naive definition, and at least in my talk I will not be speaking more about renormalization groups. Yeah, so we study the collective and emergent phenomena of many individual particles interacting with each other through the laws of quantum mechanics, dynamics, and the same individual entity organized into different phases. So this is some example. So I'll start from here. This is also the timeline in some sense. I don't know. Maybe not a time. I don't know which came before, superconductors or topological. Doesn't matter. So just for the sake of complete. So semiconductors, okay, and you can see the applications is classical computing, superconductors, the application is regular chains, and then there is the topological order, which is a completely different paradigm in phases, because it happens without what was previously accepted as a theory which explained phases, called the Landau's theory of symmetry breaking. And some of these applications actually go down quantum computing. Am I audible? So yeah, I was saying, the topological phases, they are associated, they are not associated with Landau's theory of symmetry breaking. Okay? They are spaces which happen without breaking of any symmetry. Maybe symmetry I will explain a little bit. So it is like you're changing, symmetry breaking happens when you are, say, the examples of symmetry are discrete translation symmetry, time reversal symmetry, inversion symmetry, etc. So say I take the example of a discrete translation symmetry. So it says that in a lattice there are atoms which are equally spaced and periodically arranged. Okay, so if I change something, one of these parameters, spacing or the arrangement, okay, then I will end up changing the phase. But in case of topological phases, and I will show you the first example of topological phase which was discovered, this is the quantum Hall effect. There is no change in the lattice structure, okay, but it is still a phase. So in a topological phase, properties such as Hall conductance, that's what I was saying, the first example, right? That is the quantum Hall effect. Hall conductance, maybe I will just show you the setup once. This is the setup. So you can see there is a there is a voltage applied, okay, there is a magnetic field applied to the slab which is perpendicular to the direction of the current. And because of that, there is some voltage developed which is opposite, is just perpendicular to the direction of the current. Okay. This is a 2D slab. So because of that, there is some voltage difference called the Hall voltage, and there is, if some current flows and it's not in stable state, it's called Hall current. And the quantity, which is this Hall voltage, divided by the longitudinal voltage. The voltage is perpendicular, and the direction of the current is along the longitudinal direction, not the transverse direction. So that quantity is called the Hall resistance, and it is characterized by the Hall resistivity. So in a topological case, you can see that there is some kind of a quantization, and that is obviously independent of material and insensitive to smooth deformation of the system. And the system's external deformations are considered gentle enough. So assuming that the system's external deformations are very gentle, then we can say that the topological phase is not going to change. So it's a very robust phase. Okay. And if the energy is very large, then the phase will change. In case of quantum Hall effect, if it's like a 2D electron gas quantum Hall effect state, may become a big nut, then that has associated different energies, different properties. It can be explored in those forms. So now we come to the classical Hall effect. This is usually part of the syllabus of third year or semester, sixth semester. The ones who are in second year will probably study it. I will just maybe give you some introduction to it. So this is a two-way model. So firstly, it's a model of the model of the lattice. So they are saying that the Z, here the Z, is the electrons which are in the conducting band, and the rest of the electrons are in valence band. The rest of the electrons are in the valence band. Valence and conducting band. The rest of the electrons in the core band, and there is a nucleus like this. Okay, so it's a sea of electrons. So what the idea using this model do they want to propose was that since there is a sea of electrons in a metal, okay, you can use kinetic theory in to explain the properties of the metal, like thermal conductivity and electrical conductivity, all these. So just a recap of kinetic theory classes. They treat gas molecular solid sphere, and they're supposed to move in straight line, no interaction until they collide. Okay, there is no so the average time before it travels before a collision is called the relaxation time, and all the collisions are completely random, and after a collision, what velocity the particle gets is on average equal to the thermal velocity, or at least in this model it is equal to the thermal velocity, and that velocity, its speed is equal to the thermal velocity. Okay, the speed of the velocity is equal to the thermal speed, average thermal speed, and the velocity direction is random, so net it will cancel. I'll show that. Okay. And particles which emerge after collision with a speed appropriate to the temperature of the region. So that was the kinetic theory part. Okay, so now we'll see how Landau wanted to implement that in his theory of the metals. So he said between collisions, electron-electron and ion-electron interactions are negligible. So these are fairly okay assumptions. The one in red, electron-ion interactions are negligible. Those are not really valid. Because you can see that ion is big, electron is scattered, and there will be some non-negligible interaction. You will just Electrons achieve thermal equilibrium by collision with the lattice. That is, they get the thermal velocity. This is the previous postulate in kinetic theory was once they collide with the atom, they get the thermal velocity. Mean free time is independent of the electron's position or velocity because it's mean. And sometimes it may be dependent. Some phases of matter, I think it's lasting or something. I don't know. But in this case, it's a valid point. It's not debatable. So you have this 2D equation. Most of us have probably done it. I'll just do that once again. So according to it, say your plus dt average. Okay. Equal to now assume that the electron has not collided in time dt. So the probability is dt by tau, right? Okay, so but then after it collided, since average momentum of that particle after the collision, it will get the thermal velocity, it will be random, so it will be 0, right? Plus, now probability of it not colliding is 1 minus dt by tau, and this will be f plus b plus b. FDT plus b. FDT plus because it will again get of course FDT plus b. What is p? What is capital P? Oh, it's the same p. It's the momentum. Is the dimension alright? F into dt is the momentum. Newton's second law. This is p. This is two dimension. One and this is probability. This is dimension. This is moment. It's all that. This is because I've done so this is the equation. On rearranging this equation only, I will be able to get what the equation will be in case of a magnetic field. So in case of a magnetic field, I will replace the F with the force, which is E plus E cross B. So I will just do that. That is what will give us the physics of the classical Hall curve. So it was discovered in 1879 by Edwin Hall. So V vector is the direct velocity, V is the magnetic field, tau is the mean field, and V is the electric field. So this equation you get from that. Okay. By the way, once you simplify, you take dV equal to 0. Okay. Then you get this equation on top. And then and then you take in steady state acceleration as 0. Okay, so this is 0. So you get this equation. You take the different components of the force. Okay. And now, one of the important things is writing it in the matrix form. One of the heuristic I will be actually expanding on here is the importance of the matrix. So these two terms, okay, these are your Hall resistivity, okay, and this is your longitudinal resistivity. I've written in the form which is similar to the Ohm's law. In electric field and current density form, E is equal to rho J.
Longitudinal resistivity is normal resistivity.
Yes.
Why is it 1? Just multiply the whole thing.
That's E tau by M.
Yeah, okay. Yeah.
Okay. Yeah, I think I do just in a very So if you want to get the measurable quantity, you have to make this thing by the relation NEA-VT. Here in this model it's very simple, okay, but I promise you that in when you're doing the quantum Hall effect, it will not be simple. You will have to involve some steps. Okay, and yeah, so that is the Hall resistivity. Okay, I think we have reached half point in the lecture, in the talk, and maybe next half. So this is the final equation. So I just like to point out. So this is the number density n. E is the charge. B is the magnetic field. So it goes linearly as this is what I plotted here. Okay. But now you see this graph. This is a quantum Hall effect. Okay. So this is a plot of resistivity. This is magnetic field. The blue is the longitudinal resistivity. So you see. There is some oscillation here, very strange. It peaks wherever there is a jump in the transverse resistivity. Okay. And the word quantum itself means that something is integer value.
The resistivity is normally zero unless there is a peak.
No, yeah, because these things happen at temperatures which are close to zero.
This is superconductor.
Yes.
Just as a normal conductor, the resistivity, the longitudinal resistivity goes to zero in a quantum Hall effect, in a quantum Hall setup. Superconductivity.
Because of low temperature.
Yeah, so when we talk about quantum Hall effect, there are Landau levels. In those Landau levels, there are no scattering. Because of no scattering, that's why resistance is zero. Superconductivity is something completely different.
Okay. I thought low temperatures.
There is something called minor effect and there's other stuff as well which separate superconductivity.
For now, for your own understanding, think of this as since you have not added any two-body interaction, many body interaction. So you cannot consider this as superconductivity. Superconductivity has to be with many body, at least the classical BCS theory. So clear, what you're saying is right. This is not superconductivity.
Because at low temperature, tau will be
Yes, in this case, resistivity at low temperature goes to zero, which is your longitudinal resistivity. But that is not what you have. That is not superconductivity.
okay. So the explanation is because at T goes tending to zero, the tau is very very large. So that is the quantum picture. How is it magnetic field B? This is one of the reasons why we saw that other graph. This graph. Okay, that was because there is high magnetic field. And what can we classically say about what would be the resistivity at high magnetic field? And what our intuition can tell us, so I will involve a little bit of trajectory of the particles in a magnetic field. We know it's circular. And what the quantum picture actually tells. Because we know energy is quantized. The potential is bounded. And there's Klitzing's discovery which actually proves that there is some experimentally proves that this graph was obtained by Klitzing. And how to do the problem solving to get the same results, and how we explain the graph completely. This edge effect and how we so you can think of it as orbits are larger at low magnetic fields, and that's why you can see that there is the electrons are not getting exactly bound slab of material. Okay, roughly. So they will still go through like this. Okay. And at high temperature, the mean free path is also low. Okay, that means they will collide frequently. And classically, due to the continuous nature of
Can you repeat that logic again?
What's the object?
So what I'm saying is that see the orbits are very large because of slow magnetic field. Okay, so then you can think of it like the particle is not getting confined; it is moving straight. But if it was short, then the particle will be like this inside. Right?
So you can think of it, see, the picture is like this. Think of it as the entire circle not getting completed in classical Hall effect. Just a deviation. If you have
It's not getting completed.
yeah, so that is where the polarization takes place, the all voltages happen. But when you start completing the orbit, this is still a very high orbit pictorially.
I mean, there is nothing confined.
In classical.
So you are talking about quantum, right? So there is nothing like you have to complete around your
Picture organic.
I mean,
Just heuristic. And that also in classical. I will talk about the
okay, continue.
quantum phenomena after because it is there is a problem.
Yeah. So high magnetic field just orbits around.
Yeah. That is, you can think of it like a classical. That in presence of high magnetic field, all the electrons will be able to complete the orbits and they will not flow.
So the longitudinal resistivity will be infinity.
In the bulk, in the center. That's also kind of what I'll be talking about in topology. I don't know much of that, but at least this part I'll So and also now I want to make a point. Like classically, due to the continuous nature of energy, right, we could get it straight line because energy is equal to I square RT, right? So if this is continuous, this is also some heuristic way. Don't talk. And quantum mechanics, since energy is quantized, resistance will be get quantized resistance. Heuristically from that formula, H is equal to I square RT. Any correction?
I mean,
That's fine. Please, I am very new to this subject.
It's okay, but the way you are thinking is not bad, it's not completely wrong. Just like going from this picture to now the quantum picture is, I mean, I don't know how you do it, I'm interested to see. This is not a wrong picture, but it's okay, you continue the talk, maybe we can discuss this further.
So in what kind of systems can we see this quantized resistance? So let me put it this way. In the Hall effect setup, we can see this quantized resistance if we have a very particular system. If the electrons have a z degree of freedom to move in, what will happen is that the energy levels in the z degree of freedom will all get filled up and we will not be able to observe the quantum phenomenon. I'll explain what I mean by that. But for now, the implications of what I just said is that we need to have a very fine 2D system. It cannot be just very thin. It has to literally be one particle thing, one electron thing. So that's the electron. Because we are going to get a 2D electron gas. So one example of such a system is aluminium gallium arsenide. Okay. And its heterostructure. You can make it using molecular beam epitaxy and we assume the potential to be in an infinite value in the z direction. Like that. this is assumed to be very small compared to. So all the electrons will occupy the lowest band of the confinement potential. That's how you get Fourier from. Yes.
Can you repeat that? I didn't understand how we get the 2D electron gas.
So in the heterostructure, what happens is that these potentials are the conducting, and these are the gap between them. So an electron cannot cross this huge gap. Okay, so it cannot. It will be like in an infinite potential well in the z direction.
Z direction.
In the z direction. So, and it will occupy the lowest band because that lowest band calculations is theoretical. You can plug in the number of the system and get it. You will see that it is not possible to excite it to higher band. Energy. Okay, what? This one. Energy versus
K vectors, right?
Okay, this is the graph which was using obtained when we did that experiment. Using the aluminum arsenide structure. And each was this kind of graph. You see, there are some small oscillations here. They're called just because of Mandate effect. Again, you can think of this analogy, classical optics. And then you get the for resistivity to a form which is like this. So this factor h bar by e square is called the Clipping constant in honor of the Nobel Prize winner Clipping. And here you see that your mu have to be non-negative integer. Sorry, positive integer. So you get mu is equal to 1 is there is also mu which can take fractional values. This is the fractional Hall effect, which occurs because in this integer Hall effect you do not consider interactions between the electrons, but in fractional Hall effect you consider there is some interaction between electrons. Although you still map it with the, there is some mapping which will map the lowest Landau level. I will come to what is Landau level, some energy level, to something else, okay, some fractional charge system. It's called the Spartan theory. One of the pioneers in it was J.K. Like I said in the start of my talk, J.K.
Why is there a finite width with the vector?
That's a very good question. I will explain that. It actually takes place because of the disorder in the system. So it's not a completely pure system, right? There will be some disorder.
Yeah, if it were a pure mirror, it would just be a straight delta.
It will be delta function. But because of some disorder, there will be some new states called edge states, localized states, and these other states will get occupied and give rise to the same velocity, they will remain constant. Okay, so this now I will explain. I've kept saying Landau levels. So this is how you actually get Landau levels. So remember I had mentioned matrix form in the start, like while we doing classical operators. This is more. I want to extrapolate more on the mathematical. Assuming I had to invent quantum mechanics from this experiment. Okay. I would have got a very good idea of what math I would go with, seeing the structure I used in the classical Hall effect. That was matrices. Right? So all these are actually not exactly matrices, but these are operators. similar how matrices are linear maps between Rn to Rn. These are operators which are linear maps from some subspace. There is a function the space, the vector space, there is a function space. Okay. I don't think so. You all have been taught the Hamiltonian formalism in quantum mechanics yet, right? Maybe it might be. So, okay, coming back to the Hall physics. We know that we can use a Hamiltonian formalism of quantum mechanics, and we just replace the Hamiltonian in the classical with the Hamiltonian in the quantum symbol, Hamiltonian quantum, and it is got from the Lagrange, the legendary transform of the Lagrangian. So that's why you might see that there is a P. This is called the canonical momentum, but this is the actual momentum. Consider momentum of the magnetic field as well when you do the legendary transform of the Lagrangian. Okay. So now in my system, okay, I will take Px as h bar kx. This is, you get this from de Broglie equation, because P is equal to h bar by lambda. Lambda is h bar by P. So lambda is equal to h bar by P. 1 by lambda proportional. Sorry, h by P. So okay, by 2 by some factor you will get P is equal to h bar. Proportional to K, the factor is h bar. And then now the problem is, what do we do here? So we can take different A's, okay, and that's how you get different gauges. Okay. That one of the gauges is the Landau gauge. Okay, there is another gauge called symmetry gauge where we have G into minus y plus x. Here. So assume, so now what I want to actually do here is to make this Hamiltonian come into a form which I have studied before. Okay, this is the
what is the B again?
oh, that's a vector mass, MB, right? Oh, B is the magnetic field, capital B. MB is the effective mass.
B is a function of x, y, and z.
B is not a function of x, y, z, it's constant and it's in the z direction.
So why are you written P of minus y, z?
It is vector potential.
It's a vector. Ax, ay is a three component.
Yeah.
So the ax component is minus by, and other side is a. So if you take curl of
I don't know if we can define it, we do it in any field, as long as we get the magnetic field in that direction that we design.
So you can take magnetic line. So now what my whole idea is, I will start taking some constants like these, okay, and try to reduce this. You can see from here there is a y, okay, so P, so the form is like there is a quadratic in y, there is a quadratic in P, okay, because P is equal to P vector, right, so it's Px square plus Py square, right, P vector square into D. So yeah, I have taken this, because of a y here, this will also be like a quadratic polynomial. Okay, so what I want to do is I want to make this into something which I have studied before, and that is a harmonic oscillator. Harmonic oscillator energy is half m omega square amplitude square plus p square by 2m, the kinetic energy. Okay, so this form looks like that, right? And the constants here are this. We can just rearrange and get these constants. Okay, that is the idea. You want to, and there is a particular way to solve this Hamiltonian in order to get what is the energy. In quantum mechanics, you want to figure out what is the energy, and you want to figure out what is the eigen functions of this, so that you can find out what is the wave function. Okay, eigen functions. eigenvectors, right? So eigenvectors, if you project it in the x basis, since I told you that these are operators, you can also have bases. So you project it in the x basis, you get a wave function. That's how it's related to the storage literature you're probably studying. Right? So we'll be doing this. So now you will be using some other operation called commutator and all. You have to solve this differential. That commutator also, what commutation you will be using, we will be defining another operator A in terms of P and Z. It is one of the canonical transformations you can do of the classical harmonic oscillator. Okay, which will not change the equations of motion in the classical picture. You can use that as an operator, do the commutation relations. They will actually turn out to give you what are the energy levels. What is the waveform? So I'll just write the result down. You probably see this. En is equal to n plus half h bar omega c. And this is the wave function. Okay, this Hn is the Fermat polynomial. So we can see that as in the case of absence of magnetic field, the density of states versus energy was like this. It was completely occupied, right? Density of states in 2D. Density of states is nothing but dE by dt. What? Density of states, rho is equal to dE by dt.
It was
dN by dt.
dE by dN का inverse.
Oh, okay.
Because
Yeah,
that's
so
the
it's
magnitude
dN by. But in this case, because the energy, discrete energy levels, there will be lines. This is the state and this is the energy. For a particular energy, you can have many states.
Those are energy levels or density? Like this fixed linear picture, those are energy levels or density? Excitation.
That's energy. The energy.
No, how do we get the like straight line?
So for each, this is just showing us that there are energy levels, and
So the lines are energy
particular
levels.
energy, there are many possible states.
So the lines are energy levels or how, like how is line?
Yeah,
What
yeah,
are
yeah.
energy levels?
So it's not the density of states, right?
It's plotted versus density of states.
Okay.
So per energy, how many of states are?
Huh.
Yeah.
So now we are actually moving towards finding something called the filling factor. It was now calculating here for finding the velocity and hence the current and hence what is the Hall resistivity. It's not that simple. So since we have some potential, we also have to see how many states are filling that potential. Since we are talking about electrons and fermions, right? So no two electrons can occupy the same state, right? So there will be some filling up of electrons. So for that, what I'm going to do right now is title region is I'll be finding what is the filling factor. So I can assume that there is a periodic boundary condition in the x direction. Okay, and I can say there is some length Lx over which is periodic. So I will get kx in terms of these things. Okay, and in a given now, although we can assume that the system is in the y direction, it is going infinite. Okay, I want to take a particular region in y direction with length Ly. Okay, so at y is equal to 0 to y is equal to Ly, you have your region with area Lx. Now using that evaluation of kx and this condition, okay, I can get the number of states which are present, number of states nx. Okay, in terms of the area of that region Lx into Ly divided by 2 pi L square, which you get from that.
Can you explain how you're getting at L?
Lx. No, Lx from here.
Not LX, NX.
Nx is the the number of states. So you have this. So now I can rearrange this. Take it to top, take it bottom. Kx is equal to Ly by L square, right? From that previous one. We got T x is equal to L bar kx, and we see that these wave functions are centered around the wave function. Wave functions. The wave functions are centered around this Gaussian, which is y by L minus L kx, right? So y is equal to L square k. Just substituting that. So I can get the degeneracy, okay, per unit area. Okay, so I just have to divide by area. This is Lx into Ly. So I get this thing. Now when I substitute the value for L, I will get B by phi naught. Okay, this phi naught is called the magnetic flux. It is given by Hc by L.
How is it flux? It's like constant, right?
I'm calling it flux, and there's a particular reason why I'm calling it
Flux quantum.
flux quantum.
Okay.
Yeah, flux quantum. Because I will show maybe late in the last part. I'm not very good with the last part. Please help me out. Where I will be showing how we involve the topology, the branch of mathematics, in order to understand this.
Yeah, maybe you can give the idea. Just don't derive everything and speak to that part. Define what is the filling factor. Don't derive it. Just say why it depends on inversely proportional to magnetic field, and then we can move.
So yeah, now filling factor is the density of electrons divided by your degeneracy per unit area. Okay, and that is the inverse proportion to B. If you remember in case.
What is that L like? Where did you introduce that L in the calculation?
So L is the y by L is L minus L kx was there, right?
Yes.
The center of the wave the center of the Gaussian, the wave function was Gaussian, right? So I took L y equal to kx. So yeah, this is how I get filling factor. It's equal to the number of occupied Landau levels. So it's a integer. It's a positive integer. Okay, so now we can just see this is some exercise. You can add an electric field. Okay, now it kind of exactly mimics what the system is. Okay. And again we will use the electric field because the x there will again get in the quadratic form and you can find the energy level. There will be minor changes that will be in place of just being constant because of that x here. Okay. The energy levels will be now linear in k, like this, in presence of electric field. But as such, this linear relationship of energy with respect to k will not affect our calculations much. So, what will actually now we'll study what is actually causing this the quantization of resistivity in the transverse direction, and that is because of the edge effect. We can extend this edge effect to understanding what is edge modes and other things, more generalizing. But at least in this talk, I have kept it only pertaining to quantum molecular. So you have this, again consider some confinement potential. This is because of the fact that our material, Hall slab, it has edges. something like this. Okay. This is the confinement potential plus the external potential, which will be there because of the disorder and everything. So you get your Hamiltonian. Now what we are going to do is we are going to do some perturbation. So we write your Hamiltonian as h plus h1, some perturbation.
Why are you writing Hamiltonian like a a square then plus some sum of
Oh, this is Landau.
So that's why I'm telling you can skip the mathematics and get that here. Then
So the basic idea in this is that I will be using perturbation theory in order to get a expression for the velocity, the group velocity, which is given by dE by dt. So all I have to do is calculation for what is my energy in terms of my k. So that turns out to be this. So 1 by dp del v by del x. So now I can write what is my current density. Oh, sorry, this is my charge density. Okay, and then my current density. It's not J, it's K because it's in 2D. Okay, and I can integrate my current density to get the current, linear current density. So I can integrate to get my current, and that will give me my a relation between the Iy, and since it's from the two potentials A and B, you get your V. So now what we do is we want to see how many times this potential is applied, right? Depending on the number of electrons, right? So that will be given by my filling factor. So all the electrons which are below the Fermi energy, it will be determined by the temperature of the system. Those we have to start occupying the different Landau levels that these are needed. So that's why there will be a mu multiplied with.
index you are doing zero temperature.
So Fermi level over here is not determined by the temperature but by the filling of electrons. So zero temperature.
Chemical potential and Fermi.
So in this case it's the chemical potential. Sorry. So that's how we get the transverse resistivity in terms and in this form, which is what this Lenzing constant multiplied by 1 by mu. So this is the plot, this is the expression. But now still Shreya's question, why is it flat remains? Right? We can understand why is it constant. If you want, so we can understand why there are only certain values the resistors can take. But why is it constant over the value over a particular values of magnetic field that we want to find out? So any sample there will be some disorder, there will be some doping and all. Because of that, they will have their own potential to the electrons. And you can consider again use perturbation theory to take in account those potentials. Okay. So if you consider the center of the orbit here, okay, we get these equations, and we now want to see how these orbits evolve. Okay, because I want to show that the drifting velocity of these orbits is proportional to the gradient of this force, this potential, because of the doping. Okay, so this is the math, but the end result is that the drifting velocity of these orbits, okay, is perpendicular to the potential. So if now these potentials will be like contours, okay, like this, some peaks. Okay. and these drifting velocity are perpendicular to those gradients. So around those peaks, they will be moving. Okay. So these give rise to these extend over the entire two-dimensional space, and hence they are known as the extended states. Okay. But when sometimes the energy is for given value of magnetic field, the energy the resistivity will take one value. Okay. But now since there are also localized states over the whole spread of magnetic field, the other electrons will go into those localized states. Okay. Which other than the energies which fill the particular Landau level for that particular magnetic field. Okay. And that's why the electrons, instead of occupying the next energy level and like completely disregarding the particular plateaus you observe, they will occupy the localized state. Okay, and will not, hence they will not contribute to the current. So now I'll be talking about the topology in this quantum Hall set. So I'll be talking about some maths here, this Gaussian curvature and Euler number. Initially I didn't have these two for this talk, but I got inspired very late, so I have these two topics. And this torus in quantum Euler. Why we get that torus, how we get that torus. Gaussian curvature is like if you have some surface in 3D, you place it over on that surface. You construct two intersecting perpendicular planes. Okay, and you trace the curve, okay, which is projected because of that surface in each plane. Okay, basically I'm talking about this. See, if I'm considering this plane, I'm talking about this. Okay. And if I'm considering this plane, I'm talking about this. Okay? So, the Gauss curvature is given by K1 into K2. Okay? And what is K1? K1 is a minimum in one of the curved plane, and K2 is a minimum in other curve. Obviously, it doesn't matter which plane is like first, because at the end you are multiplying them and since they compute, it's fine. Okay. Now, I'll be talking about the Euler characteristic. So, just maybe 5 minutes more. I'm also not very sure of this part, so I'll just say I will have discussion. So, the Euler characteristic is given by this number pi. So, in case of a torus, we can actually see it as a rectangular slab which we can then fold and get a cylinder, and which we can then join. Okay. In case of this rectangular slab, the number of vertices is 1. So number of edges is these two, and the number of faces is 1. The whole torus, this face. So you get for this torus the Euler number to be 0. This is like a combinatorics of surfaces. I will come to why we are doing this. You can think of like a Hall slab also undergoing some folding like this in a thought experiment, okay, to get this kind of a torus.
Is Euler characteristic the same as the genus of the torus?
Genus of the
Then it will be 1. Then it will be 1.
Then I don't know what is genus of the torus.
Genus is the
Yeah.
You use the Gauss-Bonnet theorem that came.
that is part of it. Now he is asking that E minus E plus A for a torus is 1.
It is 0.
So that's a whole
Yeah. Because for the sphere it should be 0. For then
Okay. One second. Let me just see.
I think I explained it. Vertices, there are 4 vertices, there are 4 edges, right? And one is one.
Four vertices, 4 edges. Okay. Sorry, it's one. For a sphere, which is 0. Sorry, it is. Actually, I missed this point. That okay, there are 4 edges, 2 vertices, and there is 1 edge. So it's actually.
Are you saying all your characteristics is the same as Chern's or not?
I don't
He
know
doesn't know what the genus is.
But in the Gauss-Bonnet theorem, what you have in the RHS, right? You connect your differential geometry to this combinator X part.
Because then I think you're right. That for the torus, all the characteristics is this and 0 at the number of forces something else.
I don't know what is. I only know what is the Euler characteristic.
Is it connected with the topology of the system?
Yes.
Then it cannot be 0.
If it is true. I think it is. I made a mistake. It is 1.
Will you use that? The Euler characteristic, will you use it in the topology, in the bank topology, or whatever you are going to discuss?
Like
Oh, no,
change
no,
the
no.
you are
I will actually just talk about how we do the Berry phase calculations and all
Yeah,
that.
this is not related to the very right? This
It's not related to
yeah,
the
but
Berry,
it's
but
the genus that is related.
but we use Gauss-Bonnet theorem very often.
Yeah, that is the genus. Not the
This is something else.
yeah.
Okay, so it relates the curvature to the Euler number. These are the TA is the tangential area, M is the 2D manifold, and the Euler characteristic is that topological invariant. So we can consider the whole system as a torus, okay, and assume that the Hamiltonian as H1. Now here is where I will be introducing the phi x and phi 0.
We consider the whole system as a torus. Aren't we ignoring the edge effects and stuff?
But we are doing the calculation in a different way.
What is the question?
If we are considering in the thought experiment, if we are making the slab into a torus, we are not considering the edges.
Yeah, so there is no edge.
Yeah, so we're disregarding the edge effects. But that is one of the main reasons why the resistivity was quantized or something.
Yeah, but
That edge and this edge will be different. It's not the same.
This
That
is
edge
the
gives
case.
you a jump in the potential.
Yeah.
And so it becomes easy to cross Landau level along the edge and not in the back. That is very different. I don't think it is. I don't think.
So in this, if we consider it as a torus, it won't show quantized.
Here he is just explaining the mathematics of topology, and what he has explained till now has no topology. So far, quantum Hall effect has no topology at all. So don't think of that as this as the same. Now, if you add topology to all that.
But the point is that I want to show how this quantum Hall effect made us think about the topology of the band structure of these systems. Band structure means we have one real space. Okay. Now, if there is a periodicity in the real space, okay, that is because the lattice, which is periodic, it's repeating. Okay. Then we can make the Fourier transform of each of the lattice vectors. Vector means connecting to atoms in the lattice. Okay. And transform the whole system into a K-space. Fourier transform of the lattice vector will give us another structure in the K-space. That structure for the quantum Hall system turns out to be a torus, which I said in an imaginative way is like folding up the physical lattice, making it into a cylinder, and joining edges to cylinder. We considered the same Hamiltonian of the system as H1, and there is some perturbation I'm applying delta H. And I want two magnetic fluxes. One is passing through the hole and one is passing through the other hole. Because the torus is like a tire, right? Inside there is a tire. using first order perturbation theory, we can calculate what is the ground state of the quantum system. There is some way to do that. And then we can calculate the infinitesimal change in the flux. So you can differentiate it with respect to these fluxes. Now these fluxes, they actually are periodic because I mentioned that these are quantas, right? As d by d. Is it d by d or something? I'm not sure.
H squared by.
H squared by,
I mean, what you are doing?
the flux quanta, fine one, is okay.
C by X.
H C by C. H C by C. And then there is some formula called the Cubo formula, which gives us the resistivity directly. I don't know very well what's the derivation for this formula, but assuming that there is some formula like this is how we find the resistivity. So here we can parameterize the torus in terms of these variables, and we can create an analogy to the Berry phase. Berry phase is like the geometric phase a particle obtains because of its path in the parametric space, the phase space. So
You can think of the variables as, like, let's say it completes a path. After that, it will require some non-trivial fields. If the same particle is placing on a different path, different to this, I'm going to say topologically different to this path, you will have a different effect.
but if it's topologically the same, it will have the same.
Yeah, that's all we need actually. I like this particular generation. I'm going to say this. The way I did it is using quantum adiabatic theory. Send this later.
I've shared. I just mailed you this, or I can even share the
What do you mean by the phase of the particle?
very phase.
So suppose you have a sphere and you have a vector around it.
Yes.
Now you rotate around this, so it will come to the same point, but it will acquire an angle.
Not at the equator. Any other point.
Yeah. So because of the topology.
That is what you call it.
Yeah. So I mean, you can think like that.
Okay.
So now the electron is tracing some non-trivial path. Like if it's topologically non-trivial, it will acquire some non-trivial phase. That you call it e power I gamma n. That gamma n is your phase geometry.
And by topologically not trivial, you mean it's not isomorphic to a point.
Yeah.
By topologically non trivial, you mean it's not isomorphic to a point. Is that what you mean?
That is, you are talking about points and topology.
Maybe I'm not sure.
So when two things are topologically very distinct,
Okay.
that is like, I don't know how it is defined. Okay, because I also forgot. So it's better not because what you are saying is slightly different, but I don't know the exact definition.
You are
Basically, two distinct topological sets, and there is no homomorphism between them.
Yeah, that is that. So
Okay.
you can think that a sphere, a solid sphere, and this donut, they are topologically distinct. But a donut and a cup, they are topologically the same.
Because it has one.
Yeah, and in that case, the topological invariant that defines it is the number of poles, which is the genus, or what he was calling the
all the characteristics.
Euler
It
character.
is related to the genus.
Yeah, you just checked it. It's something called 2 minus.
It's 2 minus 2.
And what you were saying was right, but that formula was slightly shady.
So also like I was talking about while we are discussing about topology, look at this image in the background. You can see like if there was a hole in between. Okay, these electrons actually they perform orbits because of magnetic field perpendicular to it. Okay, but since they cannot complete the orbit, they will just flow like this. But the ones in the center, they will not. Say, assume there was a hole in the center or something, you can see that there will be some other, on the edges of the center, that is the hole, there will be some current. Okay. So that's why we are talking about number of holes in a particular
So by this picture, and you don't have to answer this question, okay, I'm just messing with you. But it's a proper question. From this picture, the cycle in the bulb in the middle, since the orbits are completed, you derive that the resistivity is zero, right? I'm telling you, this is the longitudinal resistivity.
I heuristically said that
It is. I'm telling you. What would be the conductance?
not
Conductance is also zero in this case.
that's
So conductance and resistivity, conductivity and resistivity both are zero.
The current passes through and does not pass.
doesn't pass. That's insulation.
So that is where you get the notion of the tensor, resistivity tensor. So whenever you are talking about this picture, you have to keep that in mind, classical, because this is a classical picture, and this comes from the including one, which is a most semi-classical, quote unquote. But yeah, this you will learn now. Condensed matter going on. So pay attention to that.
So it is clear what is asking.
What is the conductivity?
Yeah, it is zero. The rho you have told is zero. Then intuitively you think that sigma will be
Infinity.
Yeah.
so there will be infinite conductors, right? But we are telling it is zero.
So what actually happens when you apply longitudinal voltage
Will
between
you apply what?
longitudinal voltage?
Infinite current cannot. That would make no sense.
If there is-
break some thermodynamics.
No, I'm asking if there is zero conductivity and zero resistivity, how much current will actually pass?
Zero. There is no current passing, but there is no scattering mechanism.
It's like a trivial solution.
There will be a voltage difference between the 2 points, but there will not be any current passing through.
In the bulk case.
And the edges there will be.
And what?
At the edges there will be a current.
The edge is the current is the
Okay.
that is what that current is because of the Landau level picture that you do. And in this simple situation is because they do not repeat the orbit, so they're skipping and leaving one taking from one.
Yeah. So from this, once you parameterize the dynamical rulers of the torus, using the periodic conditions of the magnetic flux, we can get an analogy to the Berry phase. I'll just show you. This AI of phi. Okay. And using this, we can get the Berry connection F, which is then A pi j minus A pi j by. Okay.
What is phi over here and what is phi and phi x, phi y?
Oh yeah, phi. So these are the magnetic fluxes. They are passing through the poles in the torus. So one pole is this, and the other pole is through the torus.
What are you differentiating? So on top of differentiating phi x, phi y, which are the two parameters.
Yeah.
I mean, where is this theta coming from?
Theta is the parameterized the torus system. So theta is maybe this angle, and phi is within the torus some angle.
Okay, I'm a little bit confused. Phi, there is phi.
Okay, let me say side. So within the torus there is an angle side. And
Side
along the
theta.
torus theta. Okay, theta is theta.
So that phi is different from this phi.
I said phi usually theta.
Yeah, I know, that's why you refer to it.
Okay, so once we do this, find what is the rho x, we get this expression. And if we just consider the Berry phase, the Berry phase over a complete loop, okay, of the torus, we get this integer c. And this integer c is called the Chern number, and it's a positive. It belongs to z and be an integer. 0, minus 1, plus 1. With that, I would like to tell you the applications of topological insulators. It can be used in photodetectors, phase effect transistors, lasers, and in quantum computing. Because in quantum computing we require very robust states, which are not removed because of some perturbation, minor disorder. So with that, I would like to.
just came across one quantum Hall effect. I mean, he's asking what are the different topological cases that you introduced in this? I introduced only the integer quantum Hall effect.
So here a better question would be in the integer quantum function. You're saying some topological scale is associated with it. Is that what you're saying, or because
Yeah, there is some topological phase associated with it because there is a non-zero Chern.
So what is that phase? Can you give us an idea? Because
That phase. Another thing in your third slide, right, you told something like you applied a magnetic field. I mean, in integer quantum Hall effect, you can have, I mean, phase transition without breaking any symmetry. So, I mean, if you apply a magnetic field, it will break symmetry. So once it is applied, there will be no breakage of the symmetry. If I change my magnetic field, if I change my magnetic field, can you go to this? The third step. Yeah, I mean, where you have written everything. This one. This one.
this.
Oh,
Because
sorry. Yeah. So the first point, what do you want to tell? The first line I understood. The second line. So in quantum Hall effect, when we introduce the magnetic field, we see that the number of we can occupy many more Landau levels. Yeah, that's a fact.
Can you tell me from where you got this line? Experiments like quantum Hall effects reveal that the existence of topological cases when phase transition occur without symmetry. Like, do you remember where you picked this line from? Because I'm not 100% sure that's a correct line.
Because of time, you're talking about the time. So what symmetries you are talking
Yeah,
about?
so what are
Oh, okay. Without symmetry, I meant discrete transition.
Discrete means epitaxial, the distance between.
Yeah, distance between two atoms.
So like solid liquid gas. That okay.
Yeah, because when you apply a magnetic field, you
Yeah,
really
yeah.
break the symmetry.
Yeah.
Otherwise,
No, I meant discrete transition.
Crystal symmetry.
Crystal.
Okay, so you don't have to put that. I mean,
Because
because
this is saying this to anybody in it doesn't sound very nice because the symmetries you will eventually be this one emergence symmetry translation rotational time and mostly when it comes to topology only two things you will see inversion and time reversal. You will never deal with lattice symmetry. The lattice is always fixed. Whatever given lattice it will mostly be fixed and then you will look at these two symmetries.
The motivation for me to put this line was because I wanted to say that there is a paradigm shift from
paradigm shift
Landau.
is that you cannot explain by a Landau's theory of symmetricity. You have to have a non-trivial Chern number to classify these different phases. Yeah. What will it is? So you have a topologically trivial and topologically non-trivial.
Integer.
Quantum Hall effect, there is only one thing. When you want to try to distinguish it from any other phase, you are using the Bell phase, right? And also, you're saying Chern number slightly over to it. It's not just